Hello HMS modelers, this is Avital Breverman from the Hydrologic Engineering Center. This video is a recording of a webinar that took place on September 5th, 2023. In this video, you'll hear from Greg Karlovitz about stochastic storm transposition and its implementation in HEC HMS. Enjoy.
My name is Avital Breverman. I'm a member of both the HMS and SST teams at HEC. And before we get started, I'll give you some updates. It's been an exciting time to be part of the HMS team. We released version 4.11 in mid-July, so about 7 weeks ago. And in our last quarterly webinar, we talked about all of the new features in 4.11. Today, you're going to hear from Greg Karlovitz, who's the acting Hydrology and Statistics Division Chief. Greg is going to present on stochastic storm transposition. Before we get started, I'll just go over some logistics. Everyone is muted to minimize disruptions. This webinar is being recorded, and I'll show you where it will be posted in a minute. And if you have questions during the presentation, please type them in the chat, and we will either answer them during the presentation or at the end. If we run out of time, you're welcome to email us. All right, so before we get started, I'll just remind the HEC website. You can navigate to the HMS space. Select training materials on the left, and then webinars. And you'll see all of our HMS related webinars. We provide links here in this right column to our YouTube channel, which we've very creatively renamed HEC HMS. And so with that, I will stop presenting and let Greg take over.
All righty, give me just a sec to get this going. Well, great. Well, welcome everybody. I'm really excited to talk about this topic. You've probably heard rumblings about this. I think we've made mention of this in several of our presentations recently. It's been a pretty active area of work recently for a number of reasons, and I'll talk a little bit more about those. But yeah, it's, as Avital said, a really exciting time to be part of the HMS team. I just handed reins of the team lead role over to Josh Willis, who's the current team lead. Division, so there's lots of change going on over at HEC, but I do want to promise everybody that we're going to continue to prioritize continuous improvement and customer service, so it's all positive changes. One thing I want to warn you about this presentation, I don't normally do animations. There's going to be a few animations in here, and so if you're looking at these slides after the fact, they may look a little funny. It might lose a little bit of clarity, but we've got some dense slides and I wanted to break those up just a little bit. So what we're going to do is we're going to do a brief overview just of the fundamentals of SST. There's a few other presentations that we've put out there so far that cover it in a little more detail. And so I'm going to keep this part kind of brief so we can really talk about the nuts and bolts of actually performing a stochastic storm transposition analysis in HMS. And there's quite a bit of features that came out in version 4.11 a few weeks ago that let you do this. And then I'm going to talk a little bit too about where we're going from here, the development that is either in progress right now or we have an immediate plan to tackle that's going to continue to make doing SST possible. So let's get into the fundamentals. I'm going to say modern SST because the way that we're doing business now and the type of technique that we're using contrasts sort of the traditional approach to SST that you might have seen in some of the journal papers that have floated around. They're considered kind of seminal papers in extreme flood hydrology, especially the paper that I'm going to show here from 1989 that discussed the entire idea. But SST isn't anything new. The entire idea of taking historical storms and moving them around to see what the impact on your watershed would be isn't a new idea. But really, it's in the last 10 or so years that due to the availability of data and just the availability of high quality data at a fine spatial and temporal resolution that we've really been able to do a lot more with this technique. We're able to take a much more detailed look at historical storms, understand what the spatial and temporal variability of those things is, and answer so many more questions about the behavior of rainfall in space and time, but also the flood responses to these things. Historical SST usually used data that you might get from the USAE storm catalog. So anybody who's familiar with that, if they've done PNP, PMF studies before, those are generally the worst of the worst. Those storms themselves are the collection of some of the most severe storms that we've ever identified. And moving those around answers a very different question than moving around radar-based storms that you see multiple times per year. And so what we're going to do is we're going to play with the idea of moving some more of these routine to severe storms around a little bit here. So what modern SST really is in a nutshell is we start by identifying a region, an area of similar heavy precipitation mechanics. And usually what we do is we draw an area around a watershed that we're interested in studying. And in activity, you're generally going to want to look and find a region where the tropical activity is relatively similar around that watershed. If you've got areas that are prone to well-organized thunderstorms or mid-latitude cyclones, extratropical cyclones, those sorts of things, what you try to do is you try to draw a box where the proportion and type of those storms is relatively similar. And then what you do is inside that box, you go back into a multi-sensor precipitation product, something like AORC, or stage 4, you use those products to collect up information about all the important storms that have happened in your period of record in that region. And this doesn't just include the storms that happen inside your watershed. You're looking inside that entire region that you've drawn. The data that you get for that is the entire life cycle of that storm, and you get the radar images. So you're dealing with sub-daily precipitation measurements that come from radar and satellite and gauge data, and you collect that up for every important storm. Usually you're typically looking at storm duration somewhere on the order of about 72 hours, and you collect all of these up. Then to actually perform this analysis, what you end up doing is taking each of those storms and you move them around that region at random. And when we move them, we're only talking about like the translation operation. We're only moving them in the X and Y coordinates. We're not doing any rotation of these things, any scaling of these things. We're basically saying that we believe that any of the storms that happen in this region could have happened equally likely at any other location within that region. And what you do is you take your watershed and you figure out how those transpositions interact with your watershed. And that can be how much rainfall does it receive. It could be what's the result of a flood simulation using a rainfall runoff model. You can answer a number of questions doing this, but at its heart, you're looking at a collection of storms from your period of record in a homogeneous region, and you move them around to see how they interact with your watershed. Now, in a little more detail, really what the procedure is, I refer to it, it's kind of a dense phrase, but non-parametric space for time substitution. So what we're not doing is we're not fitting any probability distributions here. But what we are doing is regionalizing our storm observations. We're looking at a big area that we think is homogeneous and getting as many important storms as we can find. And we run through this process by resampling those storm events from a catalog, preserving their space and time properties. What this does is that it avoids having to make any assumptions about how the rainfall occurs in time and space, what its frequency is, because that whole slippery question of what's the 100-year storm really causes modeling issues. When you call it a 100-year storm, what specific property of it has a 1% ACE? Is it the point maximum? Is it an area average? What duration are you measuring that over? And then you have to answer questions about what about the temporal pattern? What about the spatial pattern? It turns out it can be really, really hard to contrive a design storm that could be called the 100-year storm. And so by taking all these storms in a catalog that includes storms that might not in any respect be the annual maximum, and you transpose them multiple times per year, you may generate some sort of flood event or precipitation event that becomes a new annual maximum. And so what this whole thing really comes down to is we're going to let the data speak for themselves. We're going to let the storm properties be preserved, and we're going to try to reduce as many assumptions as we can by taking a storm and simply moving it around. Now, the simulation procedure involves is this flow chart here. And it's not as friendly as what we've already been kind of talking about here, but what you do is you start, every time you do one of these simulations, is you select a storm from the catalog with equal probability. And then what you do is you move it to a new location within the transposition domain, that homogeneous region that we've drawn, also with equal probability. And what this whole equal probability notion gets back to is a consequence of the whole non-parametric concept. We're not fitting any probability distributions to these things. We're not assuming that there's some model that describes these things. What we're saying is we believe that the record as it stands gives us a relative frequency of how these things should occur. Then every time you do that transposition, you get information from it. You either compute watershed average precipitation, and that could be at the total storm duration. It could be at some smaller duration than the total duration of the storm. For example, if you're moving 72-hour storms around, maybe you want to learn about what the 12-hour rainfall looks like. You could do that by taking the intersection of those storms with your watershed. You can either just look at the precip, but you could also run a hydrologic model. And if you're interested in doing flood frequency analysis, that's exactly how you're going to get there. And we're going to talk a little bit about both of these applications. So the simulation structure gets a little big, we're going to say here. There's a lot going on. So the whole process starts where you're going to do a multi-year simulation, and each of these are considered distinct events from one another. So we're all in an event modeling paradigm. For every year of the simulation, you're going to run anywhere from 0 to n times each year of the simulation, you're going to transpose a storm. And that count that you get is usually Poisson distributed. So you are now randomly varying the number of storms you have per year. And when you do this, you start with a storm catalog full of all of these big storms that you've gathered up, and you compute what the average rate of those storms is, and you use that as the mean rate parameter for this Poisson distribution. Then every time you run it, you gather some kind of annual maximum. So it could be the annual maximum discharge at all the locations in your watershed. It could be the annual maximum watershed average precip, but you gather up the annual maximum after making these transpositions. Now, the consequence of having a random number of these storm events per year, you're not assuming any one of them is an annual maximum. So here's an example of what happens if you run 1,000 years, the mean rate of 10. The histogram shows there's a pretty significant variation in the number of events that you might get in a year. Now think about how it rains in the place that you live. It doesn't all come in a single annual maximum event, right? Like you don't just get one event and say, well, that's the annual maximum. That's, you know, in the long record of time, it was the first largest in 105 years, so it's the 105-year storm. You get a lot of rain events, and they have varying magnitude, and that's what this entire simulation structure tries to capture, is that natural variability of the number of real storm events that you expect to see in a year. Now, to do frequency analysis, you need to run enough years to make an estimate of something like the 100-year flow or the 500-year flow, or if you're doing things getting closer to dam safety, you have rarer and rarer frequencies that you might be interested in. And so you repeat each of these years, which have multiple storm transpositions in them, some large number of times, and that number usually controls, or it does control, the rarest frequency that you can estimate, and usually you're running it out at least 1,000 years. So that you could start to estimate some of those, definitely those floodplain management frequencies, so to speak, but also out to some of the more infrastructure risking floods that you might see when you consider things like levee or dam design. And then you can repeat this process some number of times to capture the knowledge uncertainty in this process. And so you can get confidence limits around your precip frequency or flow frequency curves by running this simulation with some number of realizations in order to characterize that knowledge uncertainty. And this whole thing comes down to a big Monte Carlo simulation approach. And the only thing you need to remember, if you've never taken one of the stats classes with HEC and heard Beth Faber and myself talk about it, but Monte Carlo simulation basically comes down to if brute force doesn't work, you're not using enough. This entire process is leaning heavily on the ability to do a lot of computation very quickly. And we're going to run a lot of storm events, and we're going to see the way that each transposition and each selection of storms at random plays out. Now, what storms are, when we talk about in this context, are fine resolution representations of severe historical events. And so we look at fine resolution being both spatial and temporal scale. Spatial scale, we're generally interested in precipitation information at something like 6-kilometer around the watershed, that transposition domain. And what we do is we try to find the storms that historically occurred that would be the worst storms for the watershed we're interested in. And so in the little graphic on the right here, you can see the colored region. That's the transposition domain in here. And there's two kind of oddly shaped polygons in there. One's in gray and one's in black. They're the same shape. The gray one is the actual location of the watershed. Black one is the location of the watershed if we were to move it so that the rainfall is maximized over that polygon. So the idea is, let's find all of the storms that if I move my watershed polygon around inside the transposition domain, when I look at these storm events, I find the largest ones. It's computationally much more simple to move the watershed around to compute these averages. It also lets you make sure that the watershed always stays inside the transposition domain, which implies that when you move these storms around, you never get a storm that brings rainfall from outside the transposition domain in. Each one of those storms, we keep all of the time slice information for each of those storms. So you have, one time step is a raster, basically, if it's hourly precip. And then you take multiple events per year. Usually what we do is we take something like the top 10 events per year, top 15 events per year, or we go through the catalog and we find all of the events that exceeded a certain amount of accumulation. And I'll show an example of how this works here. So this is for a little watershed in east central Iowa. What I did here is I went through and I identified in the period of record for our precipitation data set all the storms over about 3.5 inches. The reason this number was picked was to get 440 events in 44 years of record, giving me an average of 10 events per year. And so I had to go to that third decimal precision to kind of fine-tune these things. But this is the storm center location of where all of those occurred. And in this area, basically, we looked at Iowa as a whole, and we said, I'm just going to say that Iowa's meteorology is fairly homogeneous. I'm just going to grab storms that are close to Iowa because my little watershed is about 100 square miles and somewhere in Iowa. And so what each of these storms looks like, so if I just spot. And when I move the watershed polygon to this location, that's the location that maximizes the rainfall over it. And that's how I determine whether or not this storm is severe enough for me to include. And since this accumulation over 72 hours was over that 3.491 inches, I kept that storm. The same thing can happen if I go pick another storm. This is the same thing if I slide that storm all the way up basically from here to the watershed, or the reverse of the transposition would be moving the watershed down to here. You can see one that happened right here at the edge of the boundary, but when I intersect that little watershed polygon, which used to be over here, with that storm pattern, you can see that that's fairly severe, and that's a storm that I'd want to consider. And that's how we detect these storm events. So what does this look like when we actually have the data backing it? So this is for a different watershed now. What this is when we take one storm event that occurred, this is in September of 2009, and we look at the impact of positioning it in 4 different locations. And this is a little more effective here because you can see, instead of it just being the accumulation like you have on the top row, you have each individual time slice on the bottom row. And you can see how when you move the storm around, you can think about how flooding would change within this watershed in all of these hypothetical scenarios. Even though it's one storm event, you're looking at the potential impacts that different spatial locations of a single storm event could have. Now multiply this by a very large number of transpositions and by a very large number of storm events, and you start to understand how this procedure really fleshes out the relationship between spatial and temporal patterns, intensities of rainfall, and the flooding that happens on the ground. Now, there's some fundamental assumptions in this whole process. One of them is that we can build a transposition domain where we can move storms freely from one point to another, and that they actually could occur with equal probability. That can be really hard and requires some meteorological judgment, so there's some expertise involved there. We also have to assume that the data that we gather, so all those multi-sensor products that measure rainfall, that those are adequately capturing the rainfall that actually occurred for these storm events, because that's going to be crucial. Limited periods of record that the catalog we gather is representative of the storms in this area, and that the, say, 40-ish years of record that we typically have for these multi-sensor products, that regionalized collection of 40 years is enough to describe the hazard in this area, and that it's not a sample that understates or overstates the hazard in the region we're looking at. Now, to get to flood frequency, there's a few extra things that we have to do, and the approach that we generally take, we call it quasi-continuous hydrologic modeling. So rather than trying to run a really long period of record, which is what we do in continuous hydrologic modeling, what we do is we run that model one time, and when we gather up all of the information about the states of the model, for example, how much soil moisture is there, how much snowpack is there, how much flows in the channels, how much storage is there in the reservoirs, so on and so forth. What you do is when you model one of these storm events that you've transposed, you randomly pick one of those points in time, and you say that is the state of the watershed prior to this event. And so you get types of flood mechanism. This is crucial in places especially where there's rain and snow mixtures, where there can be snow-dominated floods, rain-dominated floods, and somewhere in between. And some of those can be the worst events. Places like the state of Washington, where rain on snow is devastating. Those are places where you have to be able to model the variation of the combination of initial snowpack, initial soil moisture, and then the types of storm events that can fall on them. And so in order to do that, you do need to build a kind of a complex continuous hydrologic model to capture those states accurately. But then the simulation procedure is fairly straightforward after that, because now you have data to tell you what the variability of those initial states are. Now, here's just an example of some sample results from one realization. This was in my little watershed that I showed earlier in Iowa. I call it a toy watershed because I use this watershed for testing all kinds of neat things in HMS. The one on the left is a precipitation frequency result, and the one on the right is flow frequency result. Let's talk about the flow frequency result first. So this location had a USGS gauge that was only operating for a very short period of time, and during that, it just so happened that there was one really large flood event. And so that was the only event that this model really could be calibrated to, because there were no really other remarkable peaks of a similar magnitude that you could include in the calibration exercise. So unfortunately, what you see here is there's this gray dashed line that implies about what the magnitude of that calibration event was. So I did my best in calibrating this model, and what I did is I ran an SST simulation with this, and this uses a conventional Clark unit hydrograph. And I want you to take that idea and bury that somewhere in your brain that you can access in about 20 minutes. So conventional Clark unit hydrograph. Now with the SST, what you can see here is I compared this to StreamStats. Now StreamStats is a good regional estimate of flow frequency. It's based on regression equations. Is it perfect? No. Is it a good first guess? Yeah, generally it is. So if you're ever in a desperate need of an estimate for a flow frequency curve at a location, try USGS StreamStats first. So what we're doing here is we're comparing the results from the SST hydrology simulations for this location at the USGS gauge. And what you'll notice is that the results are perfect up to the calibration event magnitude. If you consider the StreamStats answer as truth, which you should be cautious about, they agree really, really well. And this is with the single event calibration and that catalog that we built for the state of Iowa. What you'll notice is that we underestimate the results a bit on the upper tail. And what that really comes down to is by using a conventional Clark unit hydrograph, we're not capturing some of the nonlinearity, that sort of sharpness and peakedness of a hydrograph that occurs during heavier rainfall events. And so we're underestimating the peak flow response in here. And so we'll talk in a little bit about what we're trying to do to mitigate some of that. On the left here is the precipitation frequency results. And this is basically just taking the 72-hour accumulations and finding the average over the watershed, and then finding the annual maximum for 1,000 years worth of simulation. And those are the gray dots. Now, when I went and I took Atlas 14 and I got its 72-hour averages and took them over watershed, what you're going to notice is that they're parallel to each other at the top of the curve, but that the area average is lower. And so anybody who's done a lot of hypothetical storm modeling before, whether it's for PMF modeling using something like HMR 52, or by doing precip frequency modeling, is you know that area reduction is a thing. And basically what that says is that the point maximum is always going to be higher than the area average, because you can't get sustained heavy rainfall over appreciable areas. And what this SST simulation shows us is that we can account for the area averaging that occurs in a location, like specific for our watershed, by using these storm transpositions, and accounts for the difference between what the point maximum and the area average is. So this is the exact result we expected. The magnitude of the area reduction is something for 72 hours here, I think something like 90 or 91% on average over those frequencies. There's a little bit of a frequency dependence on it as well, which is something that we want to test and find out a little bit more about. But these are the exact results that we expected to see. This is actually a really satisfying comparison. So this is hot off the press. This is from our pilots in the Kanawha Basin, so we've been showing little snippets of that watershed so far. This is just 2 locations, and I did cherry pick a couple of the better looking ones, but the results here are really, really exciting and promising. So the orange dots here are observed data, and the blue dots are from our cloud compute results from that. So this is kind of fantastic, because this uses stochastic storm transposition. It uses an HMS model to get excess precipitation, and then it's routed using RAS2D. So this captures the nonlinearity much better, because we're using that 2D overland flow result. And so that's why we're getting good agreement through the whole range of the frequency space here. A lot of folks, Dave Rosa from FEMA, cover your ears. Most folks are looking at the 100-year flood. That's about 2.3 standard deviations above the mean. That's right in this range here. So we don't have quite the refinement in this region, but what we look at when we see this is that the trajectory of these and the agreement with these is excellent. And for the most part here, what we're looking at is a difference of sample error. I mean, these things are well within each other's confidence limits. These indicate excellent responses. And the best part about this there's no calibration of the meteorological data in this case. We are literally taking these storm events out of a catalog and transposing them around. All the calibration for these flow frequency results are in the HMS model to get our excess precip correct, and then in the RAS-2D models to make sure that our runoff response and the timing and all of the shapes of those hydrographs are correct. So the meteorology in this case, which absolutely dominates the estimate of the hazard, is doing an excellent job of helping us get to these hazard estimates. So that's all well and good. How on earth would I ever crack this in HMS? So we're going to talk a little bit more about the practical side, and I'll give you a little bit of a tour of some of the 411 features that help you do this. First, I do want to give credit where credit is due. While I've been kind of the creative force behind getting SST and HMS and getting it between the agencies. It's been an exciting body of work to help contribute to the future of how we do flood hazard mapping all throughout the country. And through their funding and support, we've been able to do a lot of this stuff. One of the FEMA professional technical service contractors is Dewberry, who's been an instrumental partner in helping us process a lot of this data. And without them, we'd be struggling. And so they've been great to work with. And I do want to give a shout out to Dr. Daniel Wright at University of Wisconsin for all of his time on Shop Talk. He's kind of one of our pioneers. If you notice any of the journal papers on SST have his name on them, that's because he's been blazing this trail now for about 10 years. And so it's been really great to bounce ideas off of him and work with him a little bit informally, because it's been hard to get a formal thing together with him, but he's still very generous with his time when we want to talk shop. So to do this in HMS, the first thing you got to do is you got to get a storm catalog. And so in order to do that, first you got to determine a transposition domain. And I already kind of suggested this is a little bit of a challenge. One of the things that I've been most excited to find over the past couple of years is that there are a surprising number of meteorologists within the Army Corps of Engineers. And I think a lot of them would really love to share their meteorological knowledge with you. And I'm probably putting words in their mouth, and I can hear some of them glaring at me through the screen right now. But this does require a bit of meteorological judgment. There's some expertise involved in getting this right. There are documents and reports and all kinds of fascinating things out there that you can read about that help you make this judgment a little bit. This is an example actually from NOAA Atlas 2. This is the predecessor to Atlas 14. It's the only document that exists in the Pacific Northwest for doing precip frequency analysis on a, as a consistent product. But what this shows, I'm going to show a little example here for a study that we're about to start for the Green River in Washington, which is kind of on the windward side of the Cascade Mountains, and it's inside that red box. But one of the things that you really need to consider, things like, where does the moisture come from? What are the predominant storm tracks? What kind of things get in the way of moisture entering my system? Is there mountain uplift that causes a rain shadow effect? There's a number of complex mechanisms that really change how you make these judgments, but there's a lot of data, a lot of literature out there that really helps you. Now, after you have that transposition domain, what you need to do is you need to identify all the significant storm events in that area. And what we typically do is we use the 72-hour duration, mostly because that brackets both synoptic and mesoscale meteorology. So that's large scale, like cyclonic activity, and smaller scale, more convective type storms. And 72 hours generally been in the literature and from what we've seen pretty performant. And then you get the top 5 to 15 events per year. It really depends. You look at that low end and see if those storms are any good or not. And so you choose a threshold value for your average precip and you take a target rate. And so this is for that Green River example. So this little hatched area here kind of corresponds to some of this hatching area right up here. And hopefully you can see my cursor. It's on the eastern part of this red box. So this transposition domain was drawn here. This is the original position of our watershed in the light gray. This is for one specific storm event. We look at where would we have to move that watershed polygon to maximize the rainfall, and that's how we measure the severity of it. We go through the record and we find a whole bunch of them. And what we do is we basically rank them. We basically say, I want to know what the largest ones were, and I want to keep those. That's how you build a catalog. It's a little bit like some of those beginner art books that you get. They're a little bit optimistic about your ability to fill in the blanks. But the trick with all of this is we're working to hopefully make this a process that's usable throughout the Corps and with any of the other partner agencies or whoever wants to do this. This is mainly a data exercise. So there's some data crunching involved, but we're hoping to make the tools possible for everybody to use so this becomes something they can do. Now, getting into the nitty-gritty with an HMS. So we're out of data land, and now we're a little bit specifically into HMS here. So how you set your basin model up is really dependent on what goal you've got here. If you want to get to answering questions about things like watershed average precip frequency or area reduction functions, what you do is you pick the watershed of interest and you make one subbasin for it. And what that does is that gives you an area where you can take an average over. If you want to do flow frequency analysis, though, like kind of in the traditional like profile type approach where you get a flood frequency curve at a number of locations, you'll set your model up in the traditional way. So these two images here sort of show the difference, but this being a small watershed, it's only about 93 square miles. It's really easy to kind of highlight what you would do in a situation. This is normally how you'd set it up. This is where the USGS gauge is. That's where all the calibration was taking place. But say you also wanted a flow frequency curve down at this location. The beauty of this setup with SST is that you can get those results at both of those locations in a single simulation. You don't have to do anything different. As long as this model is calibrated and you've built the right kind of catalog for this, you can run one set of simulation and you look at the annual maximum flows here and the annual maximum flows here. Now, those might be different events, which is the cool part about this process. You do not have to make any assumptions about which storm events are going to make you annual maximum at all the locations. Think about a really complex watershed. It would be very, very difficult to come up with a storm event that causes a true annual maximum at all locations with the right frequency. And so with SST, we don't have to worry about that, especially if you're doing these flow frequency things. When you run these simulations, if I run on an average 10 events per year, say for the first year, event number 2 causes the annual maximum here, but event number 8 causes the annual maximum down here, that's okay. That's okay. And that's the beauty of these sorts of things, is because a different storm event is likely to cause a big flood here for the whole watershed as opposed to just up here. Now, the cool part about this is a lot of the work that we've done in HMS to enhance our GIS functionality makes multiple delineation arrangements easy. It's very easy to take the same base data and decide how you want to split up your watershed. So this is not an exercise where you have to jump back and forth between tools to make it happen. And so it's not as daunting to do this if you really wanted to, as a first step, do a basic delineation like this, how you would expect it to be, and then decide that you want to create another basin model with all of them lumped together. So it's very, very easy to do that with HMS's GIS tools. Now, when you do one subbasin, the cool part about this for the precip application is that you don't have to have any hydrologic processes turned on. You just need a discretization. So what that does is that tells the watershed essentially where it is in space in a way, because it knows how to intersect precipitation data with the watershed. Here, this is called a structured discretization. I think this one's using a finer scale mesh that might be 500 meter. The trick with this is that's the only process you have to have turned on, and you compute the grid cells for it, and that tells it how to apply rainfall to the polygon. But you don't have to have losses, you don't have to have surface, canopy, base flow, transform, any of those other processes turned on, which means that the model runs faster, actually, which is pretty cool. So when you're doing this, what this lets you do is it lets you transpose rainfall. It could be to anywhere within that transposition domain, and it lets you understand what the intersection of that storm event with the watershed is, and it'll compute that for you. And we'll show you how to extract those results. Now, with multiple subbasins, this is the normal modeling approach that you're kind of used to. I'm not going to highlight that too much because I kind of explained already. You would set this up, and you can get results in multiple locations. Now, let's jump from the Basin Model to the Meteorologic Model. You're going to use the gridded precipitation method. We've put all of the enhancements that let you do this inside of the gridded precipitation method. There's a few new options in 4.11 that you should kind of be aware of. The first one is this time shift method. And what that lets you do is if you take any storm event, it could have happened at any point in time. What it will automatically do is if you run a simulation using gridded precipitation with this normalized start setting on there, it will automatically lock that storm to the start of your simulation time window. So for example, if you have a simulation time window, say you're doing a simulation run, you set your control specifications so that the event starts September 5th, 2023, but your storm event actually occurred on July 6th, 1973. If you set it to normalize the start, it will automatically shift in time that storm to match your time window. Now, this is mostly meant to be used with this SST application because we're pulling storms at random that happened all across a very large period of time. I'm sure there's other creative uses for it. That's the primary use for it. If you are getting weird answers when you're using this and you're not doing SST, I suggest turning it off. Now, the star of this show is the transpose option. What this lets you do when you turn it on is specify a new storm center location for the selected storm event. Now, this lets you do a couple of different things. One of them is if you want to play this hypothetical what if scenario and you want to say, well, what if this storm happened in this other location of my choosing? It lets you do that. The other part of what it does is it lets you control those values externally. And when I say externally, I'm talking about the uncertainty analysis and the optimization trial. So anybody who's played with those features in HMS probably just got a little devilish grin and realized where we're going with this. Those coordinates now being able to be shifted in a structured way is how we achieve SST or storm maximization, because we now have a handle that we can grab and move these storms around. Now, there's an advanced option here called a bias grid. If anybody's doing enhanced transposition or wants to really get into the meat of how to do some cool transposition stuff, the bias grid lets you normalize the field, the actual precipitation values, from the location where it occurred and then denormalize it to the location where it's being moved. There's a lot of reasons to want to do this. We don't have really great guidance on what the best fields to do this with. A lot of times we use things like PRISM normal precipitation or the NOAA Atlas 1400-year rainfall. But what this lets you do is account for climatic variation within a transposition region. This still makes it important for you to draw a good transposition region, but what it does is it relaxes how strict those boundaries are a little bit, because now you can deal with things like gentle gradients of rainfall, climatically speaking. But I would be a little wary of this in really highly mountainous areas, because you don't want to be moving storms across mountain ridges and so on. But this can help you in some of those areas with a little more dynamic meteorology. Now, this is where all of the magic really happens, is in prepping the data. So we talked about developing a catalog. In HMS, we use these things called shared data components, which are stores of data that can be used where right now we're looking at about 44, 45 years of data. We're doing 10 events per year on average. You're talking about a catalog of 400, 500 events. And in that effect, you're now dealing with all of those being individual grid sets within your HMS model. So I'm going to straight up admit that those are cumbersome to manually import right now. The current practice is to write a new HMS.grid file using Python or your favorite language, but Python's kind of how we're doing it now. But in the future, I really want to make sure folks can get these things into HMS in a seamless way. And so there's plans to facilitate this in the future. The cool part about HMS, a lot of our input files are plain text, and it can be really easy to mess these up format-wise. They're really not a complex format, but you do want to make a backup of any of these files before you start changing them. But it's pretty easy to write to a .grid file dynamically and fill this information in. So if you generate all this storm data and you want to get it into the project seamlessly, you just edit the .grid file, drop it into your project, and HMS knows where to get these data right away. The keys on this is you want unique grid names that help tell you exactly what those storms were. You want to point it to the DSS file that contains the important data. And then we use the storm center X and Y coordinates that tell me where the observed center of the storm was, so that when we go back to the MET model knows where it happened, where you want to move it to, and it knows how to do the math underneath the hood to move that storm around. Now, there's a couple other tricks in here. So this is a new feature in here, is that we can enter certain parameters now, not just as numeric values, but also as strings, which means now we can enter paired data samples, random samples, that contain our storm grid names. And this is a surprise trick that will be useful to us later when we go play with the uncertainty analysis. But what this lets us do is this lets us tell an uncertainty analysis that it should vary the name of the grid that we use in the MET model, and it tells us which name the X or the Y axis. The trick being that can generate points that fall outside a domain that's not a rectangle. And so generally what we do is we generate these points first in GIS. I'm a QGIS kind of guy. I started using QGIS a few years ago, and if there's any Esri representatives on here, I have no regrets about switching to QGIS. It's free, and it does everything I ever wanted it to. So that does not constitute an official endorsement by the U.S. Army Corps of Engineers. I do have to work that in there. But this has made my life a lot easier. So one of the cool features in here, under the vector menu, if you go into research tools, you can generate random points in a polygon. And what that lets you do is if you have a transposition domain as a shapefile or a geopackage or whatever, it'll fill it with points that are uniform in X and Y. And then you can import those into HMS because we have a new sampler that lets you keep your X and Y coordinates tied together. So you'll have a list of X coordinates and a list of Y coordinates, and say the first row is one coordinate pair that defines a center that you've generated. If you use the specified values same index sampler, which is a new feature for 412 that I'll talk about in just a minute, you will be able to keep those coordinate pairs together and sample them at random from those points within the polygons that you generated in a tool like QGIS. So super duper cool. Big fan of that. Now, if you haven't used the uncertainty analysis yet, I highly suggest giving it a try. Even if you're not statistically inclined, one of my favorite parts about it is it really is a cool way to help you explore the sensitivity of parameters in your model. If you're working through calibration, you're struggling to get a handle on which of the parameters really matter, sometimes starting up an uncertainty analysis and just letting some of them vary, set it up to let your loss rates vary, your times of concentration vary, all of those sorts of things, and you get a sense of how your result varies when you allow the inputs to vary. That can be really, really useful for calibrating a model. Now, what we're going to do is we're going to use this in a little more targeted way, not so much a sensitivity analysis. And what we're going to do is we're going to set this up to move our storms around a lot. And we per year times the number of storms. If you randomly generate a number of storms for each of your years in your simulation, you just add them up. That's how you do that. And in the time window on here, you'll notice this date is far in the future. This is just so that I do not confuse in my head what is going on. If you use that time normalized feature, it will move all of those storms so that the beginning of the storm perfectly coincides with the beginning of this time window. So the trick with this, just make it long enough. The time normalization will handle the rest. This is a 72-hour time window, which corresponds to the length of our storms. Now, if you want to get precip information out, when you go into the uncertainty analysis, let me go back a slide here. What you can do is when you hit the analysis points, this is one of the things that people kind of forget to do sometimes when they set up an uncertainty analysis, hit this little gear icon, and that'll tell you where you collect output, because this generates a lot of output. If you want to do precip type analyses, you want to choose precipitation time series. And if we're doing that single basin, you're going to notice here that watershed that I had set up, it had one subbasin and one sink. Don't grab any flow results, just grab precip results. Now, if you want flow frequency analysis, you have all of those subbasins, you have junctions, you have reaches. Choose all the locations that you want to gather that up, and you want to choose outflow for that. And that's what those outputs are going to look like. In order to make SST happen, you have to make use of at least 3 parameters. You want your gridded precipitation X coordinate, gridded precipitation Y coordinate, and you want your grid name to vary. This is a little bit of what some of the settings in the uncertainty analysis look like to make that happen. If you have a rectangular domain, like we had in our little Iowa exercise, because Iowa is kind of rectangular, it's got a couple of rivers clipping it off, but the domain was conveniently rectangular. I can use a simple distribution. You can use the uniform. I specify the coordinates. I'm able to sample from those things from a uniform distribution. Now, if you use a result from GIS where you've exported those parameters, what you want to do is you want to get parameter value samples that you've created to contain your X coordinates, and you want to use a sampler like this, specified values, random same index. This is in 412 alpha, which has not hit the streets yet. You will see this soon, but that is one way to do it. Right now, what you can do is you can have it go through your specified values in order. They just go boom, 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 sequential order, and that would be the way to do it in 411 right now. And then this last one is this gridded precipitation grid name. This is your list of storms. And this one, in that case, you want it to be specified values random, and you want those to be independent. You don't necessarily want those to have the same index. Non-numeric parameters in the uncertainty analysis is new as a 411. So this is a pretty slick feature, and it actually opens the door to us doing a lot of other really cool things. Now, when you deal with the results, so we've run this result, say we've run 10,000 of these transpositions, you have multiple transpositions per year. And these storms are not annual maximum events. What you need to do is you need to go through your sample and you need to pull out the annual maximum precipitation or flow in order to get to AEPs. So if you know on average there's 10 events per year, really kind of just think of it this way. If you've run 10,000 events, take every block of 10 as a year. This is just really roughly going through this. Every block of 10 is a year, and then take the largest result out of each, and you can plot those as AEPs. And that's what you would do. In real life, when we do these simulations, we would want to vary the number of events per year because the number of events per year can actually change pretty starkly, actually, the shape of the AEP curve, so your actual annualized frequency curve. So there is a big difference here. I mentioned optimization previously. So the uncertainty analysis gives us a frequency response. This tells us when we consider all the combinations of position and storm variation, and we rank those up, we get an idea of what the AEP versus precip or flow result might be. Now, I know that what you can do with these as well is you can take an observed storm and optimize its location. And what the optimization trial will do, it will vary the X and Y coordinates until it achieves some objective. In this case, you might choose maximizing precipitation over the watershed, maximizing flow at a location. Keep in mind that this is a worst case scenario when you go and you optimize these storms. There's the only way that you get a frequency out of that is the most rainfall that we could potentially get in this catalog. And I'm going to say this is that in most applications, both in literature and what we've tried, is we're generally looking at an event when you go and do the full uncertainty analysis. That's generally something rarer than 1 in 1,000, 1 in 5,000. It really depends on the luck of the draw in the catalog. So it is a pretty rare event when you start optimizing some of those. All right, let's get on to the ongoing future development, and we'll have a moment for discussion at the end here. So there's some upcoming development we've got in the queue. Some of it is currently in a testable state. Some of it's kind of a planning phase right now. There's a few things I want to highlight in here. Some of these are related to our work with FEMA on the future of flood risk data and are related to that project. And then some of them are related to a research and development work unit. That was a new start this year. This year was our planning year, and then we've got a 3-year work unit plan over the next few years to implement a lot of this stuff. But let's talk about one of the more exciting ones. This has been something I know folks in the field have been clamoring for. With the introduction of the variable parameter Clark unit hydrograph, folks have wanted to use that with the ModClark method used with gridded rainfall and haven't been able to do that yet. So what this lets you do is this lets you define relationships between excess precipitation and Clark time of concentration and storage coefficient, which lets you capture nonlinearity. The cool part now, we could always do this with Clark unit hydrograph. Now we can do this with the ModClark method, which lets you take advantage of essentially the watershed specific time area curves that you get out of the ModClark method. This is super exciting. It's in 4.12 alpha. If anybody is interested in testing this out, please get excited for when we post our first beta of 4.12, which is coming soon, because this feature should be in there and you should be able to try that out and let me know what you find with it, because it's super exciting. But the benefit is it allows you to get that nonlinear runoff response that's crucial for doing frequency modeling. And you don't have to run a 2D model or anything to do it. You're not running the full diffusion wave solver in HMS. You're not taking excess precip out of HMS and putting it in a RAS. So you have to run a very time-consuming model. This is highly performant and does a great job with nonlinearity. Let's talk about parallelization of the uncertainty analysis. I am over the moon about this. So I've been testing this quite a bit recently. We've got a couple of concurrency issues to work out just because that's what happens when you parallelize stuff. It's in development for 4.12. I highly anticipate it making 4.12's release. There's a few small UI changes, so you may not notice anything because it's not going to be a setting or anything like that. It's just going to happen. The progress bar had to be changed to tell you what was going on because things are happening asynchronously now. But there are some serious performance gains by doing this, including with the gridded transposition. So if you have a beefy workstation computer, HMS is going to more fully be able to take advantage of that when you run uncertainty analysis. This is important is if anybody's really done a deep dive in the uncertainty analysis, You've probably seen before that you have this setting for monthly distributions for some of your parameters. Everybody knows that hydrologic processes have parameters that vary with respect to time. And one of those things that's kind of systematically obvious are things like initial states, right? What is typical soil moisture like? What does typical snowpack look like? What we can do is we can define a distribution or a set of parameters that vary by month. Now, these are totally made up. This is just for testing. But ideally, we would get values like this from a continuous simulation or observed data that we could use to define these. And then by using this random start date, what this lets us do is you can say, well, events are more likely in March than they are in October. So I'm going to get more March events. And so I'm going to typically be pulling my parameters from these March parameter sets. This was originally used in conjunction with HEC Watt's hydrologic sampler, where it could randomly define when these date events would happen. But this being just, being able to handle this inside of HMS is basically a way to unlock this feature that's been here that you would have had to have used it with Watt in the past. And so now you can do that completely within HMS. So that's going to be really fundamental for getting those flow frequency results. This is going to be post 412, but one of the things we want to be able to do is help folks be able to get the start states from a continuous simulation in a meaningful way. I've mentioned all of those initial conditions that you're going to be concerned about, but really what I want to be able to do is take a look at this continuous simulation here in the lower right real quick. So this is for moisture deficit in a specific element. I want to be able to pull this time series in and slice it up so that I have an idea of what are November initial deficits like, what are March initial deficits like, and I do that from a continuous simulation. So what we want to do is be able to create some tools that make it easier to pull those things into those monthly samplers. This is a fun one. This will be in 412 alpha. This is another way of cracking the specified value samplers. And it'll do, then it might pick row 4 and it keeps these together. You can see how this is useful if you have groups of hydrologic parameters, if you have coordinates for your SST simulations. This is a really useful sampler for doing those sorts of things. We have a long-term plan for handling simulation results and management. So we want to make it easier to define, for example, the number of events per year, number of years you have in a realization, number of realizations, and then be able to collapse those results down into like frequency result plots. This is a figure I stole from a journal paper that used SST to look at the impacts of hurricane activity over New Orleans, and they developed a point-specific precip frequency curve for New Orleans using SST. But really, the simulation structure they used here, what this gave them is, what I want to show is this kind of frequency result in the lower right. That's really what we want to be able to get to in HMS, because right now, all it knows is it's running a large number of events. That's all it's got. And so we want to get to a point where we can display a frequency. And then I do want to mention, this is my last slide before I go back to the chat and try to answer some questions. But the R&D Work Unit for Flood and Coastal Systems, it's called Improved Hydrologic Modeling of Probabilistic Storms. Really, the goal with this is to be able to provide frequency storm modeling guidance, because typical frequency storm modeling with things like Atlas 14 is not going away. It's a very useful product. The trick with it is it's been really thin on information you need to do good modeling with it. And so this work unit aims to be able to give you tools and guidance to be able to do a better job with that. So it's things like, how do I develop area reduction functions for my watershed? How do I appropriately apply temporal or spatial patterns of storm events? How do I quantify uncertainty? How do I set up my hydrologic model to be able to run these events? And so one of the cool things is SST actually helps us answer several of these questions. It helps us take historical storm events and give us an idea of what area reduction can look like. And it's not just the old TP40 curves. It's not just some of the curves you get out of the hydrometeorological reports for extreme storms. This is real storm events in your area. And they'll be set up so you can get an idea of what the orientation of the storms and its relative impact on the size and shape of your watershed might be. So SST is going to play a central role in helping us answer some of these questions. There's going to be a deep dive into a lot of literature and seeing what other folks have done good work in these fields as well. But some of the early results that we've got out of SST are very promising for answering some of these questions. And we have a plan to help develop tools for storm catalog generation, which I know is going to be the crucial bit to making this operational for anybody who wants to try it. So with that, I'd like to try to field some questions. I know I saw at least one or two come into the chat. I definitely want to make sure I get to those. stop sharing for a second here and go back to the chat. Let's see. Oh, good. Just the one question. All right. I've satisfied everybody's curiosity thus far. That makes me. It's kind of an open research question, is how appropriate it is to move the temperature fields. And we really want to get a research agreement in place with Dan Wright to be able to explore this possibility. In my opinion and my experience, I think with appropriate normalization of the temperature field, so using that bias grid option, I think it's possible. And I think it's actually prudent to move the temperature fields with the precip, because we think about the storm mechanics. A lot of them are bringing, you know, an inflow of warm, moist air. Those sorts of things definitely need to be moved in conjunction with the precip fields. And I think for things like snowmelt modeling, that's going to be absolutely crucial. So we're hoping to discover more about that. But so far, at least there is a tool in HMS that would help you take a first attempt at doing that using the bias grid. And the way I would do that is I would use like a prism normal temperature grid to try to tackle that. So we got a question from John Newton. It's highly dependent on how accurately you can define your homogeneous transposition area. This is hard with orography. Yeah, so the good resources on this, phone a friend. We are working with a lot of meteorologists to try to get there. Another thing we're doing is trying to work with NOAA actually to help us develop transposition regions, or at least a repeatable procedure for the United States. The orographic regions, you know, so we've got a couple of studies that we're doing as part of the FFRD pilots that address highly orographic regions. One of them is the Kanawha Basin in West Virginia. Another one is the Duwamish, the Green River in Washington. And so some of that is really, really dependent on your ability to figure out where the moisture is coming from, where it's going. Fortunately, something like the Duwamish, you know, we're looking at atmospheric rivers, that signal is a little simpler to get. The Kanawha is a pretty dynamic and tough place, and so we spent quite a bit of time on drawing that. But the hard part is that's not really an easily repeatable procedure by mere mortals. So yeah, that's something we hope to provide more guidance on in the future, is how to make that easier to do. The timeline on those on the guidance on the last slide. So that's a work unit that we've got that's over the next 3 years. If you want more information about that, I have a PMP, a project management plan, not a storm, that defines the timelines for a lot of the delivery. There's going to be stuff rolling out over the next few years. The first year is going to be pretty impactful. It's going to have at least a little bit of work that we can do for area reduction factors and temporal patterns and tools for doing that. So if you want some more detail on that, feel free to reach out to me about that work unit. Landon is asking a little bit about the sensitivity of the event threshold, the events per year, total events, and number of realizations. So the threshold is going to give you an idea what the smallest storm events are. And if you actually page through them, when you start getting down to a large number of storm events per year, the literature usually suggests 5 to 15 events per year, that there actually starts becoming a very small amount of variability in the more routine events. They tend to be much more uniform in time and space, and so you actually have a hard time telling those storms apart. So that lower bound isn't so much a really a controlling mechanism. Now, the thing about getting more storm events per year means there's more chances for a really large transposition to occur. And so from extreme value theory, we know this has impact on what the annual maximum look like. So one of the things we're working on is really honing in on what that sweet spot is, what that right number of events per year, and how to determine that threshold. But right now, what we're seeing with the events that are in there, the numbers of events that are in literature, that 5 to 15 range is generally appropriate. It's not really affecting which storms at the low end that we include or exclude. Transposing every event to the worst case scenario for the watershed. So that's actually a really interesting question. So there's a difference in detecting the storm events and then actually transposing them for the frequency response. So when we go through the initial exercise of screening the storms in or out, what we do is we maximize them and look at the ones that are the most severe potentially for that watershed. So it's a potential question. And so we take the largest events that would potentially affect the watershed. When we actually do the transpositions, they're allowed to completely vary within that space. And so actually what ends up happening in the SST simulations is we actually end up with a lot of transpositions where no rainfall is applied to the watershed at all, and some that directly hit the watershed, resulting in a maximized response. So that amount of variability is captured in the actual transposition simulation process. It's the screening process where we do the maximization step to get our candidate storms. That's a great question. Thank you. And I see that we're right up against 2 o'clock Central, and I want to be cognizant of time. So
So
if anybody has any questions, hopefully you have my email address. Send me an email, send me a carrier pigeon, a very carefully aimed turtle with a note taped to it. Whatever you need to do, I'm happy to answer questions.
Thank you everyone for attending. Like Greg said, if we didn't get to your question, please shoot us an email and we'll get back to you. This video will be posted within a day or two, and our next quarterly webinar will be in December, so please keep an eye out for that email. And with that, have a great day. Thank you for joining.
Thank you all very much.